Hello everybody, welcome to Integrated Circuits with Rashid. Today I'm going to explain something that I mentioned in the last video, or last episode, and I said power of the circuit increases, or power of the transistor increases when the width of the transistor increases. And somebody asked me a question and asked me to explain this a bit more. So I would like to go back to some basics and explain gradually how power increases when the width of the transistor increases. Okay. So for that, let's look into. All right. Okay. So we need to look into capacitances in a typical transistor. Understand capacitances, understand the relationship between the width of the transistor and capacitance, and then once we know how capacitance change, then we need to look into how current changes with the capacitance, and once current changes, then power change, right? So we know that power is proportional to voltage and current, right? So if current increases, power increase, right? The same thing for a circuit with transistor. Okay, so then what's the equation for current? Two things that I mentioned. One was I mentioned that, okay, this equation of current, which is current is proportional to W over L. And you can see from this one that when current width increases, our current will increase. When current increases, power will increase. Okay, so that's one aspect of it. And the other aspect is when the width increases, capacitance increase. And when capacitance increases, current increases, because current is, if you remember, current through a capacitor is proportional to the capacitance of that dielectric, the capacitance per unit area of that electric, and the change of voltage across the capacitor. So larger the change, the swing of the voltage across the capacitor, more current there will be. And at the same time, for a given voltage swing, if the capacitance of the dielectric is more, then current will also be more. This takes us to let's spend some time on the capacitance. Okay, what are the capacitances in transistor? And when I say, that's typically said in physical design to, hey, overall your transistors are getting bigger, you have a bigger standard cells, and as a result of that, there will be a bigger capacitance on the nodes, and when the capacitance is bigger, then your current will be more, and when the current is more, then your power will be more. Okay, so let's first start looking into what kind of capacitances we have in a transistor. And the understanding of that will be important to understand the basic understanding of how with width current can increase. So let's draw our transistor. Okay, an NMOS transistor is, if you remember, I don't know if I explained basic transistor functionality so far. Probably I didn't. Maybe I need to go to further into basics. I guess that's why all the books start with basics, because eventually you have to refer to those back. Um, I'm going a little bit in a different way. I start with a little bit higher level picture, and I feel like on different topics I have to go back to the basics. So anyway, this is the NMOS transistor, where you have in NMOS transistor you have this area in N plus, M plus, and your substrate, this area is P material. So and this one you have a gate electrode, and this one, let's say this is source, this is drain, this is gate. Okay, and this one here we put dielectric silicon dioxide. It's like a 2D picture, and again I'm talking about our older transistor, but with the FinFET it's a similar thing. It's just your gate is surrounded on three sides by gate instead of just at the top, but the concepts are same. Okay, so you already see that we are making a capacitor here. Okay, so what is capacitor? I don't know how much you guys remember. Sometimes the most basic things are the most difficult to explain. Let me try my best. So capacitor is as you have when you Google it or look at your books, it's made of two metals. So this is one metal, there is another metal, okay, and they have some kind of material in between. Oops. I don't know what's happened. Let's try our capacitor again. As I said, these are the two metals. Okay, and they have a material in between. Let's say this is silicon dioxide. It can be air, it can be any other thing, which doesn't allow the current to flow through this. It doesn't allow the current pass through this, but what it does is it keeps insulation between the two. Okay, and the advantage of that insulation is when you connect this, let's use the same color, to a battery. Okay, so what typically happens is this is a positive side of the battery. So what happens, the electrons which are negatively charged, so electrons start moving in this area, and I'm just showing the negative sign for electrons. Electron moves on this side. Okay, when electron moves away from this plate, electrons leave leaves a positive charge on this. Okay, similarly on this side, this is negatively charged. Okay, so electron moves on this side, and here at the same time, when this plate gets positively charged because of lack of electrons, more electrons accumulate there. Okay, so we battery will keep drawing drawing electrons from this side and keep accumulating on this side. So in other words, the charge or that you had around the battery, that's really helping build up charge over here. And it will, to a certain point, it will keep accumulating until there is no voltage difference between, say, this and this point. In that case, the whole charge will be on the two metals. Now the beauty is that, let's say, if you want to get rid of the battery, okay, let's say you want to connect it to some other circuit there. Okay, now the good thing is this capacitor has a charge accumulated on it, so now it can act like a battery. So it can, initially it was charging, and then it will start discharging and making the current flow in the other side. It depends upon the level. So this one is more positive, so this will act as more like a positive battery. This negative, so your current will start going in opposite form. So now we are discharging through capacitor. Okay, so that's the concept of a capacitor. In this one, there's the that you've seen that, okay, the charge accumulated. You remember that equation? This is the capacitance per unit area of this dielectric material. This is the voltage, okay, that you had initially with the battery. Okay, and the Q is the charge accumulated. So more capacitance, a material, here, if it is capacitance or its ability to create that insulation and have the charge accumulated on the other two sides is more, there will be more charge accumulated, right? So that's what we say, it's a higher capacitance. Okay, and capacitance is kind of fixed for certain material, like silicon dioxide will have a certain capacitance, air has another value of capacitance, depends on the material. Okay, so and your current is, we know, is the rate of change of charge, right? And Q is CV, so we can say current is, and C is, as I said, for a given material is constant, it doesn't change. So C turns it into dV over dt when you put the value of so Q, put a CV. So voltage is the one that is changing. So more voltage changes, more current will flow, right? Let's look into back into the transistor picture, and if you remember the inverter that we had, okay, PMOS. Okay, so this is supply voltage, if you remember. This is a PMOS, this is an NMOS. Okay, and I said, okay, at the output of an inverter, let's say I have a wire that goes, say, into another inverter. Okay, this is, say, a long line, say 100 micron on a chip. Then this line, okay, has some resistance through it when the current goes. This wire also has some capacitance with respect to ground. Okay. You know, so again, maybe I should explain you the, anyway, I'll explain you the wire capacitance separately, but let's, for the moment, let's say it has a resistance and it has capacitance. Okay. So this line acts as a capacitor. So we can also say that what I'll be doing is, for simplification, there's a capacitor connected to the output. Oops. So when our PMOS is on, okay, and NMOS is off, so we have this circuit. Okay. So think of this as if this was a supply connected and the other side is ground here, or in other words, they are same. Okay, so what happened, because of this battery keeps charging that capacitor. Okay, electron move in this side, okay, and current goes in the opposite side, as you know. So we were charging this capacitor. Okay, let's say our input, um, and eventually our charge, let's say 1.2 volt. So we charge it to 1.2 volt. Okay, and as soon as, now what we do is, the input signal, which was here, it was 1 0 1, right? This type of signal is coming. So when it's 0, PMOS was on. Now let's say this signal goes to 1. Okay, when it goes to 1, your NMOS conducts. Okay, now your circuit is something like this. Okay, and now you've seen that this was charge. Now as soon as you connected conducting through NMOS to the ground, which was this was source, this was drain, and this was gate. Now the capacitor will act and it will make the current flow through the transistor, and that makes the second half of the output. So when input was 0 and 1, so output, during 0, output gradually, charge. It will take a little time for the capacitor to charge. It will reach 1.2 volt, and then as soon as it goes down, sorry, that was 0. As soon as it goes to up, output will go down, because now NMOS has, so capacitor will discharge. Okay, and will stay at 0 for a little while. So this is the time during which, capacitor fully discharges, and this is the time during which capacitor charges. Okay, so you have seen how capacitor that you have studied is kind of model on the transistors. Okay, so what I explained in this one was, I was assuming this wire that you have, where you have another inverter connected. Assume, okay, let's say this is the capacitance of the wire, because it's a long line. Okay, so we'll have resistance and capacitance. And what I ignored at that time was that there is also capacitance of this node. Okay, and let's say this was C1, and there's also capacitance of this node, which is like a gate connected to these MOSes. Let's say capacitance 2. Let's call this CL, which is a load capacitance. Okay, so I'm going to spend time explaining C1 and C2. Maybe in the next video I can explain you the capacitance, or maybe we finish the devices part and later on touch the wire part. Okay, so I will explain you C1 and C2. What are the components, where those capacitance come from. All right, let's get back to our transistor. Um, Thinking of whether make sure 2D or 3D. Okay, let's start with 2D. Okay, this is your drain. I had already that picture. All right, let's try it again quickly. Source, drain, gate. Okay. And you have the substrate, which is a P material, and these are N plus and plus P. Actually, next lecture I should explain yours N P's. Let's for the moment think that okay, N is the one which had more electrons, P has less electrons. Okay. Let's look into the capacitance factor. Okay. First look into C2, which I mentioned in the last picture. This C2. Okay, let's look into that first. So that point that I mentioned was the gate connected. That C2 point was the one which was connected to the gate of the NMOS or PMOS. And let's say I'm talking about the NMOS. Okay, PMOS is typically similar, so if you understand NMOS, will make it a lot easier. Okay. So gate of the transistor, and I already explained that here in the transistor we use silicon dioxide. Okay, and how transistor works is if you think of NMOS, okay, initially before NMOS conducts, your drain, if you remember, maybe I need to explain. Okay, if you remember, before NMOS conducts, okay, capacitor is already charged. You know, so initially before NMOS conducts, your PMOS was this was the, I rubbed that one. Yeah, sorry, this was the circuit, and this node was already almost charged to supply voltage. Okay, so that means a drain which was connected to the output was already at VCC. Okay, and our source was at 0. And now at the gate we had 0 when the pin was on, and now we're going from 0 to 1. So it was 0, and now we are going to 1. So as we change the voltage on the gate, initially NMOS is off. There's no current flowing through. Let's pick another. Okay, no current flowing through this channel area. Okay, as soon as we keep increasing the gate voltage and it reaches a point which we call a threshold voltage, these channels start forming up over here. Okay, because of the capacitor action, you know, a voltage, electrons accumulate here. Okay, and then when electrons accumulate here, this node is at lower voltage, this is a high voltage, so we have current flows between drain and source. This is at plus voltage, so your electron actually start moving this, and you know that the current is the opposite direction of electrons, so current is from drain to source. Before we had this channel. Let's see, go back. Oh, too many dots, take a while. Okay, this was the capacitance. This was one capacitor, and this is another line or metal, and this point was connected, and our substrate is also typically connected to the ground. Okay, so let's keep building our capacitance model too. So if I think of, this is our NMOS. Okay, my first capacitor is between is actually over here, so let's represent that with this. Okay, capacitors over here between substrate and gate. Okay, as I increase the gate voltage, then a channel will start building, and eventually current will start flowing. Okay, now at that time, okay, since the current is flowing now here, we don't have this capacitor anymore. Okay, but interesting thing here is that this region that you see over here, okay, you probably be thinking that this will be like this. Okay, this is a source. This is exactly where gate ends, but actually it's hard to make it exactly aligned. So what happens is, in actual fact, your source goes all the way there. Okay, or in other words, there's an overlap between gate and a source. Okay, and initially this also existed. So like if I make it a better drawing, okay, gate was all the way here with dielectric gate, and source was here. So when current was not flowing, this region was also a capacitor. So this was our other capacitor, right? Okay, and similar way on the drain side, situation is similar. This is a drain, so we also have this overlap, so there's also capacitance between gate and drain. Okay, now when the current starts in over here, okay, we see the capacitance changing. So this part of the gate capacitance is not constant, because once the current starts flowing, you don't have this anymore. Okay, but as soon as we keep increasing the gate voltage more, we know that, okay, a pinch off region happens. So the kind of region is like this. Explain you in maybe next lecture. We'll go back to the transistor operation. Okay, but for the moment, okay, pinch off happens, and when that thing happens, oops, okay, then your capacitance kind of shifts. Now your capacitance between gate and drain still exists. Okay, so we have talked about this capacitance, this one, and this one, and we also know that these capacitances also change as the current through the channel changes. Okay, now there are two other capacitances I want to mention. So as I mentioned that this is, and let's change the color, everything will be same. So this is N plus and this is P. Okay, and as told you, the P is connected to ground. And before NMOS started, okay, our drain was at VCC. Okay, so think of that, that NP. So we have this type of thing. Okay, N is our drain connected to SPI voltage, much higher voltage. So we can say that this is like a positive. And our P material, his one, is connected to ground. So if you remember, what is NP? It's a diode, okay, N and P junction. And if you remember diode, I don't know, maybe I need to explain the diode too in the next video. But think of that, okay, that was really the basic device, N and P. And what happens is diode will conduct when you have a positive voltage for green, and this is a positive, this is a negative, the current will flow through the diode. Is called forward bias, the current passes. Okay, however, when N is at positive, P is a negative, you will have a reverse bias. The other one was forward. And when diode is in reverse, the current doesn't flow through them. A depletion region is created in the middle, and that depletion region creates a capacitor. Okay, we have capacitors somewhere here, cannot flow, so kind of that area charge accumulates just like a capacitor. So and you see that in this mode that our drain NP, so we have this, we have this region here which is in reverse bias. So a capacitor is formed here too, so which is this capacitor. Okay, it's the same thing with the source. Let's say in this picture, both sources at ground and the P is ground, but with both them at ground, you will not have that the same diode forward bias. It will be reverse biased. Okay, so there will be still some capacitance, though less capacitance in this case. Or capacitance is the same, the amount of charge accumulated is there less. So there is a capacitance here as well. So there's another one. So right, you see 1, 2, 3, 4, and 5. Hopefully I've covered all the components. So these are the 5 capacitances that exist on a transistor. Okay, and the capacitance is calculated with, okay, you have capacitance of the dielectric, which in the gate case will be a capacitance per unit area of silicon dioxide, and for these diode junction reverse bias, it will be like a capacitance per unit area of the junction. So capacitance, total capacitance is whatever the basic capacitance, and you multiply with the area of the two metals, the two capacitors, area of the capacitor formed by two metals. Okay, so if you think again, sorry, I've discussed a lot of capacitance here. I know it could get a bit confusing. I wasn't expecting that much detail, but as it comes, I start explaining it. If you remember, the one, okay, this is a good example. The one where I said there is an overlap. Okay. In that case, how you calculate the total capacitance is, whatever the capacitance of the silicon dioxide plus the whole area. It's a time for my favorite 3D picture. Let's do quickly. Yeah, all right. Okay, so this was should make a new color. This was silicon dioxide. Okay, and it's the top level is gate, and underneath we have a different color. Right. This one you don't see, right? It comes out. It's like this. So you see, for another color, it's gonna be better. It'll be this one. So this area, which is where you have the two, this metal, which is the gate one, and the one at the bottom. Okay, that is the length and width of that area. So let's say, what was that? This let's say this was the length and this was the width. Okay, so area would be, capacitance would be whatever the dielectric capacitance into length and the width. Okay, and what is length? Length is really, I should not call length, is let's call it any other number, x or b, y or z or whatever. Let's call this is x, and this is so this w is really the width of the transistor. Okay, so bigger the width is, mean more area will this be, means there will be more capacitance. Okay, you got that? Similarly, if there's a more this overlap area, there will be more capacitance. Okay, so you understand now how the width can contribute to more capacitance. So this was for this and this. Okay, let's talk about the other one. Sorry, this was about the, sorry, I'm wrong. 1 and 2. 1 and 2. I was explaining here. Same thing with 4 and 5. If you remember, this area, it really depends. If it's a larger width of the transistor, you will have this area more. Different color. More is the bottom area that will be making a capacitance with this substrate area. Okay, so hence more width, bigger width, more capacitance mean more current means more power. Okay, and same thing with the 5 and 4. Okay, and it's the same thing for this main one. More gate area you have, more this whole area you have, more is the width, bigger will be that area that will be that the gate will make a capacitor with the substrate. So means more capacitance means more current. More current means more power. Now one thing you probably be thinking, let's start a new one, it's a lot of mess. You probably be thinking our voltage goes from 0, let's say battery was 1.2, like it goes 0, 1.2, 0. Voltage is still 0 to 1.2, but as soon as your voltage changes, this is where most of your charging current or discharging current, depends where you are, increases. Like the current will be something like this, something like that. Okay, so with more capacitance, more width, the magnitude of this will be higher. Okay, and we know that power is the multiplication of this voltage and this. So at a given point for 1.2 volt, you will have much higher current. So your power will be more. Okay, so power is again the current that flows, is dissipates. When the current flows, power is consumed, and that results into making the device hot when so many millions or billions of these transistors get hot, you need a cooling of the chip, and if you need a bigger cooling, okay, you need to put a fan on it, which can be an option in desktops, can be an option in laptops, but we cannot put it on your mobile or iPads or tablets. So that's why we want to keep, and even for very slim laptops, okay, you don't want power to go very high, so we want to make sure our power is low, and that's the compromise you have to make when the width is bigger. And I explained you earlier, when the current will be more, when the current is more, that means it's really, transistor is faster, right? It carries more current, information quickly, strongly, so which is good for frequency. You can run it much higher frequency, but when you run it high frequency, you also consume a lot more power. The leakage power is a bit different. Maybe I'll touch it in another video. I think that's enough for today. Hope you like it. And if you have any question, please write that in the comments. And see you next time. Take care. Bye.